Hi, I'm Randy Appel, and I'm your Regents tutor. And in this lesson, you're going to learn everything you need to know for the Regents about organic chemistry. Now, a lot of you may have older siblings, or maybe your parents or friends that say, in college, organic chemistry is the hardest unit. You're so lucky. In high school, it's so easy. Well, part of that's true. It is really difficult in college, and some people find it really difficult in high school. But we're going to make it really easy for you. And the great news about organic chemistry is the reference tables. You can use the reference tables for almost 75% of all questions on organic chemistry. It's really that important. So if you really just know the reference tables, you're almost all there. First, let's talk about what an organic compound is. An organic compound is any substance that contains carbon. All carbon-containing substances or compounds are organic compounds. There is actually two exceptions. If carbon is with an oxygen, just an oxygen, like an oxide, like carbon dioxide or carbon monoxide, that's not organic. If carbon is part of the carbonate ion, which is a polyatomic ion, like sodium carbonate, that's not organic. But every organic compound contains carbon. And in general, 99% of organic compounds contain carbon and hydrogen. So as long as you understand that all organic compounds contain carbon, you're set. Now, what makes carbon so special? Well, what makes carbon so special is it can form chains, rings, networks, any way that a substance can bond, carbon can bond that way. So it can form really long chains of even carbon atoms. So really, really, really long chains, and that enables us to have many, millions and millions of organic compounds. In fact, there are much more organic compounds than there are inorganic compounds, which is a substance that doesn't contain carbon. Organic is a substance that has carbon in it, except for those two exceptions. Now, the key to understanding carbon and organic chemistry is understanding the number 4. That's right, the number 4. Carbon has 4 valence electrons, which means carbon needs to gain 4 electrons, which means carbon always, 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 always has 4 bonds. Sometimes they say, which is the correct formula for this substance? It has to have carbon with 4 bonds. And it could be single bonds, like this. This just means it's bonded to something else. It could have a double bond between carbons. But then each bond has, this carbon has 1, 2, 3, 4. And this carbon has 1, 2, 3, 4. It could even be triple bonds. And then it has 1, 2, 3, 4. And this one has 1, 2, 3, 4. So understanding that carbon needs to have 4 bonds is the first step you need to understand organic chemistry. Very important. Now we got to talk about properties of organic chemistry. Like all substances, there are properties to them. And the first property is the bond type. Organic compounds, since it has carbon, carbon's a nonmetal, nonmetals tend to form not with each other covalent bonds. Organic compounds contain covalent bonds. And I'll even go one step further. Organic compounds contain nonpolar covalent bonds in general. Does that mean every single organic compound is nonpolar? No, but in general, organic compounds form nonpolar bonds. Now, if you need some more information on nonpolar bonding and covalent bonding, go to the concepts on those terms. But for right now, you just need to know that organic compounds form generally nonpolar bonds. How about solubility? Well, remember like dissolves like, and if you're not sure, go back on the concept on factors that affect solubility. But like dissolves like means the same bond type will dissolve in the same bond type. So if organic compounds are generally nonpolar, then they generally will only dissolve in nonpolar solvents. So water, which we know is polar, will not dissolve organic compounds. So we say that organic compounds are generally insoluble in water. How about conductivity? Organic compounds are molecules because they're formed covalently. Molecules do not conduct electricity because molecules do not have ions. So organic compounds do not conduct heat and electricity. And melting points and boiling points. Organic compounds are held together by covalent bonds, which are generally weaker, so they have low melting points and low boiling points. One thing I wanted to just talk about with conductivity, there's one exception to this rule. Organic acids, because remember, acids are electrolytes, and if you don't know what an electrolyte is, go to the concept on electrolyte. But electrolytes are conductive. They conduct electricity. So organic acids conduct electricity. But in general, other organic compounds do not conduct electricity. And the speed of a reaction. Covalently bonded substances tend to react slower than ionically bonded substances. So organic compounds, since they're covalent, react slower. And they react relatively slowly. Now, within any kind of substance, but especially organic compounds, there are three formulas you need to know about. And the three formulas are the molecular formula, the structural formula, and the condensed structural formula. And I'll show you a molecular formula. Let's say you have a substance C3H7OH. C3H7OH. That's a molecular formula, because that just tells you what you have, C3H7OH. It tells you the number of carbons, number of hydrogens, and number of oxygens. Now you may be thinking, why is the OH separate? Why can't you just say C3H8O? Well, because organic substances, you have to recognize the functional group. And you'll learn what functional groups mean a little later in the lesson. So the molecular formula in this case would be C3H7OH. The structural formula is actually what it looks like. So if it's C3H7OH, it's actually going to look, the structure is going to look like this. There's three C's bonded together. Each C has an H attached to it, except for this one, which has an OH. This is the structural formula to this molecular formula. This tells you how many you have. This also tells you how many you have, but it tells you how they're arranged. Molecular, structural, and the other kind of formula they could show you is a condensed structural formula. So it tells you both. Not only what you have, and not only how it's written, the structure, but it's condensed. You don't have to write this big thing. You just break it up, though. There's CH3 here. There's CH2 here. There's CH2 here. And then there's an OH. And this represents the condensed structural formula, which is just based on the structural formula. It's just condensed or made a little smaller. And those are the three types of formulas you're going to need to know about when we talk about organic chemistry. So if you keep those three formulas in mind, things will be a lot easier down the road. Structural formulas. Okay, the next thing I have to teach you about is something called a hydrocarbon. Now you're probably thinking, well, at least I hope you're thinking, hydrocarbon, hydrogen, carbon, well, carbon. Hydrocarbons contain hydrogen and carbon only. Very important. I'm going to say this clearly. Hydrocarbons contain only carbon and hydrogen. Now, there's a whole table that goes over hydrocarbons. Table Q shows all the different types of hydrocarbons. There's three groups of hydrocarbons. There are alkanes, alkenes, and alkynes. Now, when you're talking about hydrocarbons, you know that they only have carbon and hydrogen, and there are different properties to the alkanes, the alkenes, and the alkynes. Three of them are listed here. Well, actually four. First one is the name. The alkanes end in ane. As you can see here, ane. Alkanes end in ane. The structural formula for hydrocarbons, they're all single bonds. Notice that they're all single bonds. That's what alkane is. They have all single bonds. And the last thing that they show you here is the formula for how to determine whether something's an alkane. What this means, and a lot of students have trouble, it says CnH2n plus 2. And what that means is however many carbons you have, N, you have 2 times that many plus 2 hydrogens. So let's say, for example, you have 3 carbons. That's C3. How many H's would you have? Well, 2 times 3 is 6, plus 2 is 8. So the formula for that alkane would be C3H8. And that's the general formula for alkanes. Another thing that's not on this table that you need to know about alkanes is that since they're all single bonds, they're saturated. Anytime you have all single bonds, it's saturated. It's a little different than a saturated solution, but saturated means it has all single bonds. S, S. Single, saturated. Good. Next is alkenes. Alkenes end in ENE. As you can see, ENE. Alkenes have one double bond. One double bond, as you can see right here. Alkenes have the general formula CnH2n. CnH2n. So if I have 3 carbons and I want to know if it's an alkene, it should be C3, and then 2 times 3 is 6. Oh, C3H6. That's an alkene. And then and since it has double bonds, we know that it's unsaturated because only if it has all single bonds is it saturated. So since it has a double bond, it's unsaturated. And alkynes, the last one, end in YNE, and it has one triple bond. One triple bond. And the general formula, CnH2n minus 2. So if it has 3 carbons, 3 times 2 is 6, minus 2 is 4. Oh, okay, so it's C3H4. And that's the alkynes. Now, when you're dealing with alkynes, remember, this is not all single bonds. So is it saturated or unsaturated? Well, SS, single saturated. Oh, well then this must be unsaturated because it has triple bonds. Very important when you're dealing with alkanes, alkenes, and alkynes that you know that the only ones that are saturated are the alkanes. They do not tell you that in the reference table. What they do tell you is that it has single bonds, and you have to remember that all single bonds are saturated. So all alkanes are saturated, and alkenes and alkynes are unsaturated. Next thing we have to do is name hydrocarbons. To name hydrocarbons, we have to go back to a different table. We go to table P. Table P shows the prefix, and it says organic prefix, number of carbon atoms. So let's say you forgot that organic compounds contain carbon. Just come to table P, and it says number of carbon atoms. Now, remember that alkanes end in ane, alkenes end in ene, and alkynes end in ine. And the number of carbons determines the prefix, or what it starts with. So, if it's an alkane with 3 carbons, that means it's C3H8, because of the formula CnH2n plus 2. So if you see C3H8, you know it's an alkane. Well, it has 3 carbons, so we go up to table P, and we find the number of carbon atoms is 3. Then we go to the prefix, prop. Therefore, this substance is called propane, because alkanes end in ane. So this is propane. If it had 4 carbons, it would be butane. 5 carbons, pentane, and so on. Do you need to memorize the prefixes? Of course not. They're in your reference table. So to name alkanes, you just need to know how many carbons there are and end it in ane after looking at table P. For alkenes and alkynes, it's similar, but it's one step harder. It's the same thing. It ends in ene, but you have to say where the double bond is. So let's say you have 5 carbons. So the formula, the molecular formula for for a 5-carbon substance that's an alkene would be prop, because 5 carbons is prop. Actually, 5 carbons is pent. Excuse me. Don't make the mistake, actually. It's very important because pent and prop sound alike. And when you come to the table, just make sure prop is 3, pent is 5. So if you have an alkene with 5 carbons, it's C5, and then it's H2N, so it's H10. Now, to name it, you have to tell where the double bond is, and that's where it gets tricky. So that's the molecular formula. Let's say I gave a structural formula. Let's say it looked like this. Five carbons. Rest are hydrogens, because remember, in a hydrocarbon, it's all carbons and hydrogens. Now, why are there no H's here? Because remember, there has to be 4 bonds to each carbon. So this carbon has 1, 2, and then 3, 4 here, and same with the other one. Now, the way I name this, you know it's 5, so it's pent, so it's something pentene. But you have to tell me where the double bond is by numbering the carbons. Now, you can number the carbons 2 ways, from left to right or right to left. But there's only one correct way to do it. And you have to number it so that the number where the double bond is on is the smallest. So if I number from this side, it would be 1, 2, and the carbon and the double bond would be on the 3rd carbon. But if I numbered it from the right, it would be 1, 2, and the double bond is on the 2nd carbon. So I'm going to number it from this side. And again, I pick the smallest carbon that it's attached to, and this becomes 2-pentene. And that's how you name alkenes. It has the double bond, so it ends in -ene, and you just have to tell me the number of the carbon that it's on. If it was on this one, we'd number it the other way, and that would be 1-pentene. And alkynes are exactly the same way. You name alkynes ending in YNE, and you just number where the triple bond is. And I'll give you one example. You have 4 carbons. You start from this side again because the triple bond is closer to this side. 1, 2, 3, 4. And this would be called 1, and this 4 is bute, 1-butyne. 1-butyne. And that's how you name alkanes, alkenes, and alkynes. The next thing you have to know about naming hydrocarbons is what happens if there's a functional group. A functional group is a group off of the original carbon chain. And it's actually not much harder, but it's actually a little harder. And the way you name functional groups is the same prefixes. 1 is meth, 2 is eth, 3 is prop, but it ends in YL. It ends in YL. So let's say you have a substance like this. This represents, well, you tell me, is it an alkane, alkene, or an alkyne? Do you see all single bonds? It's all single bonds, which means, therefore, it's an alkane. The first thing you do when you see, you don't just name it with 5 carbons. Because the first thing you have to do is go to the longest carbon chain. And the longest carbon chain is right here. That's the longest carbon chain. Now there's something falling off of the longest carbon chain. And that's a functional group. When it's not part of the longest chain, it's called a functional group. And you circle your functional groups. This functional group has 1 carbon, and it's a hydrocarbon, so it's meth. Remember, functional groups end in -il. This is a methyl. And just like double bonds, you have to number which carbon it's on. Well, if you number from this left to right, which you could, it would be 1, 2, it's on the third. If you number from right to left, 1, 2, 3, 4, it's on the second. So again, we're going to number from right to left. And this would be called, you have to tell me where the methyl group is, 2-methyl butane. The key is just remembering that you have to number where it is and knowing where to find the longest carbon chain. Okay. That's hydrocarbons. Now we're going to get to something a little more tricky, although it would be more tricky if you didn't have your handy reference table. Table R. Now, sometimes the functional groups are not carbons, just CH3 or C2H6. It's not IL groups. It's actually the functional groups on table R. Now, table R, you really just need to know table R to understand organic chemistry. And that's how you understand how to name everything. So I'm going to take you through each class of compound, but I'm going to take you through it using the table, because you're allowed to use the table on the Regents, so you better get familiar with it. The first thing is if you have an organic compound that has a halide, such as fluorine, chlorine, bromine, or iodine. Those are called halides, or halocarbons. With those, the functional group represents FCl, Br, or I. You name it the same way you named hydrocarbons. You find the longest chain, and you look. This is 1, 2, 3 carbons and a chlorine. And you also have to number where the chlorine is on the chain. This is the condensed structural formula. On the screen, you could see the actual structural formula. There's 3 carbons. There's a chlorine on the second carbon. And you see they're named either fluoro, chloro, bromo, or iodo. This one has a chlorine, so it's a chloro. It's on the second carbon, so this would be called 2-chloro, and since there are 3 carbons, propane. Don't memorize how to name these things. Come to the table. If there was a fluoro, it would be 2-fluoropropane. If it was a bromine, it would be 2-bromopropane. And if there was an iodine, it would be 2-iodopropane. And that's how you number it, and name it. Excuse me. The next functional group is when there is simply an OH off of a chain. Just an OH. That would be called an alcohol. Do you have to remember that? No. Alcohols, how do you name them? Alcohol ends in, oh wait a minute, all alcohols end in OL. So you see here, this is 1-propanol. That's how you recognize it's an alcohol. 1-propanol is the alcohol. How do you know it's the alcohol? Looking at the formula? Well, you see there's an OH. The way you name it is you find out how many, 1, 2, 3 carbons, so it's prop. The OH is attached to the first carbon, so you number it 1, and then propanol. If there were 4, it would be butanol. You don't have to remember that alcohols end in OL. You just have to come to the reference table, R, and look for the OL. And these are the general formulas. You know it has an OH, and it has a general formula, ROH. And R just represents a bonded atom or group. So in this case, the R here represents this whole entire group of carbon and hydrogens. And that's alcohols. Ethers are even easier. Ethers, the next one, has an O in the middle of 2 carbon chains. An O in the middle of 2 carbon chains. 2 R's, which represent carbon chains for ethers. How do you name it? Well, you take the hydrocarbons you have on each side, because on each side of the O, here you have 1 carbon, and on the other side you have 2 carbons. And you use those functional groups we talked about. 1 is meth, 2 is F, 3 is prop, etc. In this case, you name it methyl, il, they all end in il, methyl, ethyl, ether. So this substance is methyl, ethyl, ether. Let's say there were 2 ethyl groups on each side. There would be an ethyl, and then an O, and then an ethyl, as you can see on the screen. That would be, you wouldn't say ethyl, ethyl, ether. you would actually say diethyl, 2 ethyls, ether. Diethyl ether. Aldehydes. Oh, one more thing about ethers, excuse me. You do not have to number ethers because there's no number there. The ones you have to number, you see it on the equation and you see it on the reference table. Aldehydes end a chain, ends a carbon chain with a C double bonded to an O and an H. So a CHO. Sometimes they'll just write CHO and they won't write the C double bonded to the O and the H. But in general, it's a CHO and you see it here. And the way you name aldehydes, you see it ends in AL. Why are there no numbers there? Because you don't have to number where the CHO is because it's always at the end. So we don't have to tell you where it is because you know it's at the end. It ends in AL. There's 1, 2, 3 carbons. 3 is prop. This represents propanal. And you have to be able to recognize these substances apart from each other. You have to know what an aldehyde is. And that's what an aldehyde is. Use the table. The next one is a ketone. You may be saying, wait, the ketone looks a lot like the aldehyde. But it actually doesn't. Because the ketone has a C double bonded to an O in the middle of the chain. So there's 2 carbon chains on each side. The way you name those, ketones end in one, O-N-E. Ketones end in one. And the way you name it, you tell me what number carbon that C double bonded to the O is on. So this has 5 carbons. 1, 2, 3, 4, 5. And again, you could see the structural formula in the slide. But there's 1, 2, 3, 4, 5 carbons. You want to number it. So again, the smallest carbon has the C double bond to the O group. So I number from this side, 1, it's on the second. If I numbered it from the right, it would be 1, 2, 3, 4. I don't want to do that. I want to number from the left to make it the smallest. So it's 1, 2. 5 is pentanone. Ketones end in -one. And you recognize the ketone again because it's a CO in the middle of a carbon chain. And you do have to number it. An organic acid, and we talked about organic acids before, an organic acid has a COOH at the end. This is what it looks like, C double bonded to an O and an OH, but they could also just say COOH. And it would just literally say, as you can see on the screen, COOH. And that's an organic acid. And the way you name that's easy also. Oic acid. Oic acid. So there's 1, 2, 3, propanoic acid. Do you have to number it? No. One reason, because there's no number here. The second reason is because it's always at the end. You just have to know how many carbons there are and how to recognize it. And the last major one you need to know how to name is an ester. An ester has a COO in the middle. So it's literally a C, O, and an O in the middle of 2 carbon chains. This one gets a little tricky. The way you name this is something ill, something O8. And now how you put it in there depends on what you have. So you see here, this is the group that recognizes it as an ester. COO. The part that's touching this O is this group right here, 1C. The part that's touching this O is the ill group. Now I mean by ill, not the ill you're thinking of, YL. So there's 1C, that's meth, so that's the methyl part. Methyl. So remember it's something ill, something O8. So the ill part is the part touching the O. 1 carbon, this is methyl. The other part is the part that contains the C. C, there's 1 here, and then 2 and 3. So there's 3 carbons attached to this part of the group. And this is the O8 part. So this is called methyl propanoate. Methyl propanoate. And you just have to know that you name the ill part touching the O and the O8 part touching this C. And you name every ester the same way, depending on how many carbons there are on each side. And it's important to be able to recognize an ester. The amines and the amides, they don't ask too much about and how to name. You just may have to tell the difference between the two. And you see an amine has an N in the middle, and then 3 groups attached to it. Some 3 groups, whatever it is. Just an N. An amide has a C attached to an O, some other group to the left of it, an NH attached to the right of it, and an R, another group coming up from the N. You don't have to memorize this. It's all on the reference table. Just be able to tell, using the reference table, the difference between an amine and an amide. That is naming the functional groups. That's a lot of stuff, but remember, you need to know all this stuff and you have the table. The next thing we need to talk about is an amino acid. An amino acid is not on this table, but you need to know what it is. An amino acid has a carbon in the middle, it has an acid group, and it has an amine group. So it has a carbon, as you can see, a COOH. It actually has an NH2, and you can see it on the screen, and then 2 other groups, 1 hydrogen, and then 1 R group, which could be anything. So it's a carbon in the middle that has a carboxylic acid, which is the COOH, the acid part. It has an amine part, which is just an NH2 here. And then it has a hydrogen, and then some other R group, which is some random bonded atoms. And the last thing we need to know about this is when you're dealing with boiling point in organic compounds. So when you're dealing with boiling point, the more carbons you have, the higher boiling point, because it's more bonds you have to break to boil it up. So that's all we need to know with naming, with organic functional groups, hydrocarbons, and all the good stuff. The next thing we have to talk about are isomers. Isomers are substances with the same molecular formula, but different structure. So the number of atoms are the same, but the structures are different. The way you tell an isomer, if they say which of the following is an isomer of this substance, you take that substance, you count up all the substances, all the C's, all the H's, all the O's, and you find out which answer has the same number of C's, H's, and O's. Now, there are a lot of problems on the Regents with isomers, so you're going to be able to go over a lot of problems for isomers. And remember, listen to the video explanations when you're going over isomers. But what you need to know is isomers have the same molecular formula, same number of atoms, but just different structure. And for the alkanes, butane is the first example of an isomer. You can't have an isomer of propane, because you can't write it any other way than propane. If you had, well, you can see on the screen, if you have 3 carbons in a long chain, 3 carbons in a crooked chain, it doesn't matter. It's still propane. The first type of isomer you could have would be for butane. And an example of an isomer of butane would be methylpropane. Methylpropane, as you see there. And the reason why you don't have to number where the methyl's on is because it can only be on the second group, the second carbon. Because if it was on the first or the third, then it wouldn't be methylpropane, it would just be a butane again, because the longest carbon chain would be 4 carbons long. So that goes over isomers. And the last thing I have to teach you are the series of organic reactions. There are certain organic reactions you need to understand, and they're reactions revolving around organic substances. The first one is combustion. With combustion, you're taking a hydrocarbon, organics, or any organic substance, you're adding oxygen, and you're always producing carbon dioxide and water, and a huge amount of energy. It's always the same. It's an organic compound plus oxygen gives you carbon dioxide and water, and you're releasing energy. And the first couple of reactions on table I, you could see on the screen, represent combustion. The next reaction is fermentation. Fermentation is the process by which we make alcohol. We take sugar, which is C6H12O6, which is glucose. We break that down into alcohol and carbon dioxide. And you just have to remember these. It's when you take sugar or glucose and you get an alcohol and carbon dioxide. And now you know how to tell if it's an alcohol because it contains an OH, as you could see on table R. So you really need to know table R very, very carefully for all parts of organic chemistry. The next reaction is saponification. Well, what does it sound like? What word do you hear in saponification? Soap. Saponification is making soap. And all it is, you just have to remember, it's taking a fat plus a base and getting a soap plus an alcohol. And the alcohol is actually called the glycerol. But you need to just know it's a fat plus a base giving you a soap and a glycerol. The next kind of reaction is esterification. Esterification is the process by which we make, what do you think? An ester. So we take an acid plus an alcohol and we produce an ester and water. And the way you could tell esterification is you're producing an ester. An ester is being produced. So if you look at the products and you see an ester, you know it's esterification. And you can actually see in the slide, you could see the ester being made by removing the water. When the water is removed, the bonds combine and you get your ester, as you could see. Other organic reactions, addition. Now with addition, you need to understand that with addition, you're actually adding something in. So with addition, you always have an unsaturated hydrocarbon or an unsaturated organic substance. So with addition, what you're doing is, you see this substance in the screen, you see, let's say it's ethane. You see the double bond? Addition, it's unsaturated. You would be adding something, breaking the double bond, and where that double bond was, you now add what you wanted. So let's say you have ethane, and you want to add chlorine. What happens is the Cl forces the double bond to break, and the Cl just bonds on, and that's an addition reaction. The way you tell an addition reaction is you have an unsaturated substance, and you're adding to it to produce only one product. So you have two reactants and one product. Substitution, on the other hand, is two reactants and two products. With substitution, you have a saturated hydrocarbon. And with a saturated hydrocarbon, it's just one thing is substituting another. So let's say you have ethane. Not ethene, but ethane. With ethane, you take one of the H's from the ethane molecule, and you substitute one of the Cl's from the Cl2 molecule, and you get chloroethane. And you don't have to number where it is, because it can only be on the first carbon, because whether you number from left to right, it's still the first carbon. So this shows a great example of a substitution reaction. Remember, two products, two reactants, all single bonds. And the last kind of reaction we're talking about is polymerization. Polymerization sounds really complicated, but it's actually quite simple. Polymerization is just making a long chain of something. A long chain of what? Well, it depends what it is. Let's say you're making starch. Starch is found in plants. Starch is many glucose molecules put together. So starch is a polymer, and all the glucoses are each individual monomers. So a polymer is many monomers put together. And you can have addition polymerization, where you add things at the double bond. Just need to memorize this. Or you could have condensation polymerization, where you add it by removing water. And that's your polymerization. And that's really it. So I hope you learned a lot about organic chemistry. It's really important that you understand everything we went over. Go over all your questions, even if you know the answer and get them right. Go over the explanations and come to the chat if you need to. But that's all of organic chemistry. Hope you learned a lot.